Recording's rolling. It's Wednesday, February 11th. Okay, so here's top scientist for simple harmonic motion. So Uncle John made that list. Of course, yesterday we started on fluids. So you guys have chapter 13 puzzles. So my plan is to do some of these and clap you guys eventually. Right. So anyway, that's in your hand. If you want to start reading those, see what kinds of questions that you might get. Alright, so going down this list yesterday, we got to about right here. We didn't quite hit conservation flow or Bernoulli principle, but I'm going to do some review with you guys today from what we did yesterday. Have you guys solve few puzzles and then eventually work towards here. Okay, and then of course your 8th classroom unit 8 is open right now. Tentatively have the due date set as this coming Tuesday. You guys know that there's no school on Monday or Veterans Day. Alright, so let's look here. Alright, so look at this. I don't got involved, don't need that. Alright, so here guys, what Greek letter is this right here? Rho, yes, Greek letter rho, and physics is going to stand for density, which is an intrinsic material property. It's ratio of mass to volume. Right, so many kilogram per cubic meter. Guys, how about water? Guys. What's the density of water in kilograms per cubic meter? How many kilograms are there in a cubic meter of water? 1,000. 1,000. Yeah, 1,000. Yeah, so when the metric system was being devised hundreds of years ago, right, that ratio was established so that people could define what a kilogram even was. Okay. Ooh, Archimedes' principle. So this tells you the magnitude of a buoyant force. Actually, it really goes hand in hand with this. Maybe we should do this one first. Right? So these two different concepts. Right? There's how much pressure do you feel? Say if you dive down to a pool, the deeper you go, the more the pressure. Right? Because if you dive twice as deep, what happens to the pressure on you? Twice as much. So double. Right? Okay, and then there's this related concept, which is what is the upward acting force on you from that surrounding fluid? That's called buoyant force. Okay? Really similar looking expression. They said they both involve the density of surrounding fluid. They both involve the gravity field of the planet. Okay? And then if you multiply by your depth, you get the pressure. If you multiply by the displaced volume, that's equal to the buoyant force. Okay? Actually, this one on the left side is Archimedes' principle. So let's see that. Okay. Let's see. Do something here. Yeah. All right, here, guys. Let's figure this out. The depth of the Titanic. We got about 3,800 meters down in the ocean. Right. And let's what do you think is a little bit more dense, freshwater or saltwater? Yeah, saltwater is a little bit more dense. Let's ignore that. We'll just go with the same density. Right? It probably won't be that much different. So 3,800 meters deep. I wonder what is the pressure? Let's find that out right now. Right, so you guys got your notes out, right? You guys got notes, paper out? Yeah. And so depth of Titanic is 3,800 meters. Question is, what is the well, I could say what's the pressure on it, but I'm gonna word this two different ways. What is the absolute pressure? Absolute pressure. And what is the gauge pressure? There's two other different ways to take that. So we got I give you guys a picture. Maybe here's the ocean surface. Here's the Titanic down here. And then the ocean floor. And so I'll say H equals 3,800 meters. Okay, now you guys told me salt water is a little more dense than fresh water. We're going to ignore that and just say the density of the water is approximately 1,000 kilograms in a cubic meter. Okay. And let's use gravity field is about 10 meters per second squared. Okay, so okay. Here, I'm gonna say let's start with the gauge pressure. All right, or maybe you guys memorize this just by using it, or looking at your notes from yesterday, or looking at the AP equation page. What's a good expression for this? Yeah, rho GH. Rho GH. Okay. All right. let's go 1,000 kilogram per cubic meter. Let's go 10 liters per second squared. And 3,800 liters. Guys, what's the units on that number? Huh? Pascals. Yeah, pascals. All right, so great. So big number of pascals. Maybe I want to convert this to atmospheres. Like, how many atmospheres is this? So pressure gauge is 38 million pascals. Okay. But how many atmospheres equals how many pascals? Here, look at your notes from yesterday. 1 atmosphere is how many? You guys remember 101,000 pascals? Okay. Remember, 1 pascal is a 1 Newton weight on 1 square meter. That's 1 pascal. Right now, the atmosphere you're sitting in this classroom, it's about 100,000 of this. So maybe you. All right, so let's put this all together. It's 38 million divided by. I'm looking at.
Yeah, no, that's about pieces.
375 atmospheres. Now that's the gauge pressure. Guys, that ignores the fact that Earth's atmosphere is also pushing above. Okay, so that's just the gauge pressure. So guys, what is the absolute pressure?
376.
Is how much?
376.
376. Yeah, because you have to add the additional atmosphere that's pushing above. 376 atmospheres. Okay. And that's relative to a vacuum. Ooh, right. So remember, gauge pressure is you just subtract out the atmosphere, like the smallest reasonable pressure that's around. Okay. Okay. So the pressure differential between where you're sitting in this room and the Titanic, it's like 375 atmospheres. Okay. But if you also include Earth's atmosphere pushing down, well, you get 376. Right. All right, guys, good there? All right, so you got that. Another good one to do here, guys. Let's do this iceberg question. This is a real classic question. It's good exercise. Okay. So I'm going to change it from an iceberg to a block of wood. And so I got this block of wood floating in a lake. Okay. Let's say the wood density is equal to, let's say 700 kilogram per cubic meter. Water density, we'll just use the same. Let's call it 1,000 kilogram per cubic meter. Okay. And I want to know what percentage of the wood block is above the water line. All right, so let's get a 3-body diagram going on this block right here. All right, what's one force on that block?
Gravity.
Yeah, its own weight going straight down. So I'll say that's the mass of the wood times gravity field. That can be weight, mg. Buoyant force. Yeah, buoyant force. So that's F sub B, buoyant force. Ooh, sounds like Archimedes principle. Okay, so that's equal to what times what times what?
Mass of land.
Yeah, mass of the density of the surrounding water, density surrounding fluid, the water, times gravity field times displaced volume. Okay. The displaced volume is just, well, I just hashed it right there. Just the part that's underneath the water, the submerged part. Okay. It's the framework. We could use force equilibrium, right? The sum of the forces goes to what?
Zero.
Yeah, zero newtons. Okay. There's two individual forces, right? One down, one up. So let's say buoyant force minus the weight of the wood goes to zero. Okay, so we got density, water, gravity field, displaced volume. Minus. Now, I'm going to make a substitution right here for the mass of the wood. What is the mass of the wood in terms of its own density? Yeah, density times volume. So this would be the density of the wood times the volume of the entire wood block. Right, and then I still got this gravity field multiplied. So that goes to zero. Is there any questions so far? All right, give you guys a bit of head start from that point. Hopefully everything up to that point makes sense. See if you can finish it.
Wait, I have a question.
Yeah.
Can you explain what you just did again? Because you took the mass times gravity. Like, how did it turn into that? Yeah.
How did this turn to this?
Yes.
Okay, so I know that density is equal to mass over volume. Therefore, if you want to solve for the mass of something, it's equal to its own material density times its own volume. Okay. Okay, so this mass wood became density wood, volume wood, and this gravity was always just there to make this weight like a force. All right. So you guys know the target question. You want to know how much of that wood is actually floating above the surface of the water. That's what you guys are trying to get right now.
That's much lower.
Anybody got the answer? Oh, yeah, check.
Wait, above water or under the
water?
water? Above?
Yeah, above the line.
30%?
30%. Yeah, just got it. It would be 30%. Okay. Guys, quick rule of thumb. Do you guys see that what's the ratio of the densities?
30%.
Like 70%?
Yeah.
Right, you guys get it? Right. So 70% of the block is always going to be submerged because of that. Okay. Therefore, the other 30% is going to be above. Okay, so you can kind of immediately know what the answer is going to be. Of course, it's better to be able to derive that and show why. And so here, let's today's adventure though. And so I can say density, water, gravity field, displaced volume is equal to density wood, volume of the entire wood block, then gravity field. That gravity field cancels. So I could set up a ratio like displaced volume compared to the volume of the entire wood block, right? So this divided by this, right? Right. And if I cross divide this over, then I'm going to cross divide this density the other way. So that works out the density wood over density water. Okay. Now that's 700 over 1,000, and the units cancel. So I call it 70%. Okay. Now remember, that's the part that's submerged compared to the entire block. Right. So the question that this actually answered is what percentage submerged? Okay. But the target question is how much is above the water line. So it's like 1 minus that. Okay. So then percent above would be the whole block, 100% minus 70%, which is 30% is going to be above. Right, and that answers the target question. Right, you guys decide to solve a floating block of wood or a floating ice cube. Just do that. Right. That. Ooh, let's do this hydraulic lift. So yesterday, you guys were Pascal's principle says pressure is transmitted and diminished. We're afraid. I pulled my cave system real fast from yesterday. Um, here it is. Here it is. You guys remember this cave system from yesterday? Right, so these people are walking around on land, right? We got trees up here, right? And so, oh, hey, there's a cave down here. Oh, there's some water in it. This guy, hey, there's a cave over here, some water. Right? They send down some divers. They realize it's all connected underneath. Right? Guys, does this water line have to be the exact same elevation?
Yes.
Yeah, it sure does. That's really Pascal's principle. If these divers dive down each 10 meters, do they feel the same pressure on them right here? Same, yeah, same pressure it has to be. Okay. So that's Pascal's principle. And you can use this to create a hydraulic lift. Let's do it. Right, so I'm going to throw some numbers at you guys. Right, everybody get a good look at that? It's probably in class 2. There, good. All right. So we have a hydraulic lift. Okay. What input force on hydraulic lift will lift the car? Right. Right, so let's get a small piston on one side, a large piston on the other side. I've got hydraulic fluid in the middle. All right, give you guys some numbers here. Let's say this diameter is 10 centimeters. Let's say this diameter is 100 centimeters. Let's say the weight of the car is 20,000 newtons. That's the weight of the car, 20,000 newtons. Right, so over here on this input piston, I'll do force input. Right. So what's the input force? Right, any question about the premise? All right, so give you guys a bit of a head start. Right, let's start solving that. Does anybody know the answer at this point? Yeah. So I do know that it's the same pressure everywhere in this hydraulic fluid. And pressure is the ratio of whatever what again? Yeah, so force compared to area. Force compared to area, right? And these are different forces and they're different cross-sectional areas. Actually, this force we're trying to solve. So I'll do F input divided by something equals pressure equals, oh, and I know the force output is 20,000 newtons acting on some area on this side. Yes, what's looks like my pistons that this cross-sectional area is roughly circular, but let's call it a circle. Okay. Yes, what is the area of a circle based on its diameter? Because I gave you diameter. How does that go? Okay, yeah, you guys square the diameter and multiply it by what? Pi over 4. Yeah. So it's pi over 4 diameter squared. Um, just for good measure, maybe I'll convert this to meters. Guys, 10 centimeters, how many meters is that? 0.1 meters. Okay. By the way, if you forgot to convert from centimeters to meters, it would make no difference anyway, because it's the ratio that's going to matter. So that factor would cancel anyway. Okay. But then over here, let's go pi over 4, and then, 100 centimeters. Could I just call that 1 meter? Okay, and then square that. Do it like that, right? Okay. What cancels on both sides? Yeah, pi over 4. Great. Okay. So really the pi over 4 again just has to do with the shape of the circle, or the fact that it is a circular shape. Okay? But if you treat these as like square cross sections, then the answer would be the same, and that's maybe evident. Also evidence why that would cancel out. Okay. So we're solving for this input force. The other thing I gotta do is cross multiply this 0.1 squared. Guys, what is 0.1 squared? What's that? 0.01? Yeah, okay, and this meter squared is gonna cancel. Okay. So I'm gonna end up with newtons, force to describe the force. Okay. 0.01, is that like 1 over 100?
Yes.
Okay, so what's the answer? How many newtons of force do you have to push down with over here? 200, yeah, that's 200 newtons. That's the answer. 200 newtons. Awesome, thank you.
All right.
All right, you guys, that's all hydraulic left. Guys good?
I can really cry by a lot.
Let's back here. This YouTube. Let's do a few of these. These are fun. Yeah. Alright, so here, let's start with some trivia. Let's start with some trivia. What if I have a tube looks like this? Let's say this side is open to atmosphere. Let's say this right here is a perfect vacuum. Let's say all of this right here is water. Okay. That could reasonably look something like that, right? I got a perfect vacuum here. I got water. I got this end is open to the atmosphere. So there's going to be a height differential, isn't there? Do you guys see the left side's been sort of like vacuumed up? Yes. That. See if you guys remember this from either yesterday or last semester. Guess what is that height differential equal to? Yeah, about 10.3 meters. 10.3 meters. So that, but 10.3 meters, that's pretty tall. That's about as tall as the school. So
Yeah, that's Friday.
back hundreds of years ago, people would build devices like this, but they said, well, let's not use water because this height differential is so big. Another way to contextualize that is if you dive down to a swimming pool 10.3 meters, it's like you've added additional atmospheric pressure on it. I forget if we talked about this yesterday. Guys, what's a liquid that's much more dense than water? I'm thinking of an element on the periodic table. Mercury. Let's do kind of the same experiment, except we're going to replace the water with mercury. Okay, so
Did you use your mom?
maybe look something kind of like this. So same thing. Let's have this be a vacuum. Let's have this open to atmosphere. But this time, this is going to be liquid mercury. Okay. There's also a height differential, but guys, since liquid mercury is so much denser than water, how do you think these height differentials compare? Like the one with mercury is much what?
Smaller.
Smaller, yeah, much smaller, right? So it's a lot smaller than 10 meters. Okay. So what is it for Mercury?
3.
Hmm?
Should be 1. Oh, simply.
76 centimeters. 76 centimeters. At sea level. If you went way up in the mountains, like to Denver, Colorado, then that number would be even smaller than that. Down here at sea level, it's gonna be 76 centimeters. All right, so you guys get with the yeah, that was a little bit of trivia. That's a good warm up. Let's do a classic YouTube open to the atmosphere on both ends. Open to atmosphere, open to atmosphere. And that is something like this going on.
Oh, really?
That's what they are. It's like an example. What is the first thing? AirPod.
That was for
Now Parsons. Let's talk about
Oh, really?
Oh, no. Basically,
Really.
Okay, let's have this be water. Let's have this be some mystery oil. Mystery oil. Okay, we don't know what the density of it is, but I'll give you guys some heights. Let's say this, I'll call this H1. Let's call it 10 centimeters. And let's say this H2 over here is let's say 5 centimeters. All right. Yeah, and I want to know what is the density. Right, so find the density of the mystery oil.
Okay.
And these are both open to atmosphere. Okay. All right, so give you guys a little head start. See if you could set up an equation that could officially answer that question.
We're having this. Use the function.
Thanks, bro.
No, guys, I want to tweak one thing. Can I change one number? Let's go back a little bit. Let's not do 5 and 10. That seems a little too boring. Let's change this to a 6. I want to see what happens if I change it to a 6. Let's do that. Okay. So let's do 6 centimeters and 10 centimeters. Is that okay?
Yes, sir.
By the way, the fact that I just increased that a little bit, maybe here's a good critical thinking step. Guys, if I guess I could raise this all the way up to 10, right? Maybe like 9.999. So like that. Could that be? Okay. Because once it hits 10, then this would have no difference in density than the air, right? So the fact that I increased that from 5 to 6, what did I just effectively do to the density of the oil? I made it a little bit what? A little bit less dense. Yeah, it's a little bit less dense.
We said that.
Okay. Right. You guys got an equation set up?
Yeah.
So give you guys a hint here. What I might do is make another dash line. And I would say, what do you know about the pressure right there compared to the pressure right there? Is it the same pressure right here and here?
But not.
Yeah. Is it the same pressure right here and here?
Yeah.
Yeah. Yeah. So it's the same pressure, left arm and right arm of this YouTube, all the way up into that point right there, and then everything above that. Well, now the pressures are different. Okay, but right there, pressures are the same. So I think it's a P left equals P right. Okay, so the pressure at that point on the left is that pressure on that point on the right, same pressure. Okay. And what is this gap right here? What's that height change? 4 centimeters. So maybe we call that H3. Let's call it 4 centimeters. Right. So, the pressure on the left side, that being the atmosphere above pushing, pressure atmosphere, plus density of the water times gravity field times 4 centimeters. 4 centimeters. Is that correct? Okay. Now on the right side, I've got, well, the atmosphere also pushing, pressure atmosphere, right? Plus density of the oil times gravity field times what number goes right here? 10 centimeters. Yeah, 10 centimeters.
We're making another ratio.
Right. Is that okay? That set up? What cancels out right away?
Gravity.
Well,
The atmosphere.
okay, yeah. First, you have to cancel out the atmosphere. Right? Yeah. Now, true. After you cancel out the atmosphere, as a second step, you're allowed to cancel out the gravity field. Yeah, that's also true. Oh, guys, do you guys know a value for density of water?
1,000.
Yeah, 1,000 kilogram per cubic meter. Got 4 centimeters. And that's kind of mixed and matching units, but this will be okay. Okay. Density oil for solving for, and 10 centimeters. The unit centimeters cancel, so even if you convert that to meters, then you're right either way. Okay. Right, so you can tell me what's the density of that oil?
400 times.
Yeah, 400 kilogram per cubic meter. Or guys, another way you can describe density is something called specific gravity. Here, maybe I'll jot this down. Specific gravity. Which is say what's the density of this material compared to water? Okay. So you can call it 0.4. Right. I doubt AP is ever going to throw this term at you guys, but you might hear it in the wild somewhere. So if you do, it's like 4/10 out of 1. All right, so you guys get so far. Get so far. All right. All right, so we got a pretty good. I think that's about where the bell was bringing yesterday. I gave you guys one where it was also half to one side. The equation is a little different. All right. Here. I got a demo question for you guys. Here, you guys see this paper right here? Alright, so I'm gonna go as far as I can in class today. Guys, if I blow a stream of air over the top, I'm gonna blow horizontally. The paper is basically horizontally, it's kind of length. I'm gonna blow a stream of air horizontally over the top. Here, you guys ready for this? Alright, so I want to see a show of hands. How many of you guys think what's gonna happen? Is the paper gonna be pushed down or is it gonna be vacuumed up? What do you think? Pushed down or vacuumed up? Okay. It's show hands time. How many of you think the paper is going to be pushed down? Who says push down? Push down. Who says vacuumed up? Vacuumed up. Okay, looks like most of you guys are saying vacuumed. Well, let's find out. Let's see. It does vacuum up. Do you guys see that? You guys see that? That was interesting. I blew a stream of air over the top and it vacuumed up. Have you guys ever stepped in the shower? Here's a shower curtain right here. You guys ever turn on the water from the shower head and the curtain like actually vacuums in? You guys ever seen that too? It's same phenomenon. Okay. Why is that? Why do we get some kind of moving fluid and somehow the pressure decreases and it has this vacuum at that? Okay. So that's called Bernoulli's principle, by the way. But before I can explain Bernoulli's principle, first we got to go over conservation of flow. That's going to lead into it. All right, so let's do one thing at a time here. Right. Say I got this pipe system with a bunch of water flowing through it. Okay. Now, guys, do you think that, well, if you see conservation of flow, do you think if you quantified, like 50 gallons per minute over here. Do you think it's also 50 gallons per minute going through this other pipe? Right, or it's all the same pipe system, it's just different diameter pipes. Guys, everybody look here. You gotta think deeply about this. Think deeply. Right. If it's 50 gallons per minute here, it's 50 gallons per minute everywhere. Now, of course, in this class, we're not using gallons per minute. We're gonna use what per what? Cubic meters per second, right? Because that's the units that consistent with everything we've been doing. Right? But it's the same everywhere. Now, if I cross or rope off some volume. You guys see a very thin cylinder there, right? Like a thicker cylinder here. But guys, could those reasonably be the same volume cylinder? Is that okay? Right? Because the thin cylinder in a large diameter pipe, and the thick cylinder in a small diameter pipe, that could be the same like volume of water roped off. Right? Okay. And then let's get this flowing. And if the flow rates are the same, the volume per time is the same. Right? But guys, how do you get the volume of a cylinder? It could be what times what? Yeah, this cross-sectional area times this thickness. Is that right? Okay. So that's what I did right here. So I got volume per time is the same in both sections of the pipe. Okay. Volume I broke down to this cross-sectional area, which is like a circular shape, okay, times the thickness of that cylinder. Okay. And it's going to move that far in an equal interval of time. Okay? Okay. So guys, are these T's the same? Are these T's the same? Yeah, but that's the only thing that's the same. These areas are different, these X's are different. And they match the picture. Okay. But let's do this now. Let's rope these together. Guys, what is distance over time called in physics? Velocity, like V for velocity or speed. Okay. So I can say this. This cross-sectional area times the speed of the water going through is equal to this different cross-sectional area times a different speed. Huh. Right? Okay. Notice I'm talking about areas, not diameter. Oh, but we kind of did this before with the hydraulic lift. It's really common to refer to pipes by their diameters. Oh, we have a 4-inch pipe or whatever. But guys. If somebody ever tells you out in the wild a 4-inch pipe, they're referring to the pipe's what? Diameter. Right? So if you want to play an equation like this, first you have to find the cross-sectional area. And what is the area based on the diameter of a pipe? Yeah, pi over 4d squared. Okay. Now the pi over 4 bit can cancel, but if I gave you diameters, you would have to square the diameters. Is that right? Guys, could you say this? Guys, hang tight with me. Could you say diameter squared times speed equals diameter squared times speed? You could also do that. Okay. How about this? Is the fact that we're going from a large cross-sectional area to a small cross-sectional area. So A2 is smaller than A1. What happens to the speed of the water going from the big pipe to the small pipe? Okay, show of hands. How many of you think the water has to speed up when it goes into the small pipe? Who says it has to speed up? Who else thinks it has to speed up? Yeah. You see the water speeds up? Right. Okay, so now we have some speed difference going on. Okay. Now there's another little complication here. Guys, do you guys think that water is basically not compressible? But like it has a constant density. Like if we're talking about water here, I think it's pretty much 1,000 kilogram per cubic meter everywhere. You can call that incompressible, right? If you did have a compressible fluid, for example, air could be compressible, you would also have to consider density. But I rarely ever see this consideration. I don't think AP would ever have you consider the density. So let's just ignore this green box. Let's just focus on this gold box. So we've got A1 V1 equals AT V2. Okay, let's get that. All right. And so you can have different speeds based on different diameter cross-sectional areas within the pipe system, okay, to prevent conservation of flow. Okay. All right, and that's going to set up eventually this Bernoulli principle right here. Bernoulli principle. Okay, so, all right, what if you have diameter cross-sectional area change? And let's add another twist. Let's say there's also a height change. Okay. And I'm going to throw a fish in here, and the fish is swimming around. Okay. Hey guys, this fish swimming around the pipe system. Do you think the fish feels different pressures at different points in the pipe system? Yeah, different pressures at different places. Okay. Yeah, guys, even if the water wasn't flowing at all, what would happen to the pressure just going upward? What happens to the pressure? Has to decrease, right? Like if you go from the bottom of the pole to the top of the pole, I feel the pressure decrease. Okay. But let's throw on this factor also of the speed of water changes. What if there was just a horizontal pipe? Would would the fish still feel a pressure change going from here to here?
Oh. Yeah.
Wait a minute. I know you know that that's the case because I just blew a stream of air over this paper and it vacuumed up.
Yes.
So you guys just saw a demonstration that a moving fluid causes the pressure to do what? Increase or decrease? What vacuums something? Decrease, huh? So a moving fluid is going to cause a decrease in pressure. Okay, and how can you sort of derive that? And I'm going to derive this with you guys from conservation of energy. You guys remember conservation of energy? Okay. So in your notes, I recommend you either write small or hold your paper landscape, one of the because we're going to make a big equation here. So I'm going to say sum of energy at one point in the pipe system equals sum of energy at a different point in the pipe system. Okay. And we're eventually going to turn this into pressure, but one step at a time. So let's say some internal energy, just call it E naught, some internal energy, maybe thermal energy or whatever. Okay. Plus, guys, what's another form of mechanical energy we're using? Yeah, kinetic. Okay, so could you call that 1/2 mv squared? Okay. What's another form of mechanical energy? Yeah, have potential mgh. Yeah, gravitational potential mgh. Or some bit Earth gravitational. Okay, let's just work with those three. Some generic energy, potential, and kinetic. Okay. And let's say another point in the pipe system is maybe a different mix, but the energy has to be conserved. So it's a different internal energy plus a different mgh plus a different 1/2 mv squared. Okay. So they're different. I better throw some subscripts. So say initial over here. Oh, whoops, sorry, I'm going to say final. There you go. Final. So we got initials and we got finals. Or you can say sub 1, sub 2. Okay. And what I'm going to do with this 1, 2, 3, 4, 5, 6 term equation is I'm going to divide every single one of these terms by volume. So V could stand for volume. Okay. Right, that right? Now guys, what is this right here? What is mass over volume called? Density. And that shows up there, 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 and there. Okay, see those 4 places? Okay. How about this? What do you think energy over volume is? I'll show you guys. It ends up being pressure. So I could have some initial pressure here. This refers to pressure. Okay. Mass over volume. Here, I got well, that'll be rho for density. Rho g h naught plus 1/2 rho v naught squared equals pressure in the final condition plus rho g h final plus 1/2 rho v final squared. Okay. That right there. It's called Bernoulli's principle. Right? Right, that right? Right, so it's basically conservation of energy, but now in terms of pressure units, we're thinking in terms of pressure. Right. So now you guys told me that okay. Here, now we could throw some numbers here. We got limited class time, so I'm just gonna keep this big idea from here to the end of the class. Okay. Guys, let's say you have so many pressure units, so you throw some numbers in here. Okay. The fact that when you go to raise your elevation, doesn't this rho gh2 isn't it larger than this rho gh1 because of its larger height? Okay. So you can sort of think of like stealing pressure units. And if that's true, what happens to this internal pressure? It has to decrease because this term increase. Okay. How about this? You guys know from conservation of flow, the water also speeds up here, doesn't it? So you guys see this green term on the end? Isn't this V2 much greater than this V1 from conservation of flow? Therefore, doesn't this 1/2 rho v squared also steal pressure units? And what does that further cause this P2 to do? Gets even smaller. Yeah. So the fish feels a decrease in pressure going from left to right for 2 reasons: going up in elevation, but also going to a smaller diameter pipe. So guys, before you take off, we've got a Venturi effect here, Right, so similar to Bernoulli. Okay, here's a really classic physics question. You guys, last thing. If you have a big tank over to the atmosphere and you run a pipe down and open the pipe, how fast does the water go down? Now, you said Bernoulli principle. We'll have to still walk through this every day. But at the end of the day, the answer ends up being the same as the answer to the Galileo question. You guys see that? All right, we'll have to pick up that part of the story a different day.